I'm just go ahead and start. Good morning, good afternoon, good evening, everyone, wherever you are. I hope you are having an amazing time. Welcome to the 16th International Symposium on Networks and Chip. My name is Maddie Niktas. I'm one of the program co-chairs of this year's NOCs. I'm just going to walk you through some logistics and introduction to this year's program. Before doing that, I would like to introduce this year's organizing committee. Of course, I'm just speaking on behalf of everyone. The work in this year's conference is the result of all the efforts and the great work of this whole team. Sergey and Josh as general co-chairs, myself and Mikhail as program co-chairs, Radu as our steering committee chair, Azin as our special session chair, Salva as our web chair, Puna and Jeming as our publicity co-chairs, and Alirez and Abhijit as our virtual logistic co-chairs. So just to walk you through some of the statistics and the submissions for this year's conference. What was different this year compared to other years is that this year we actually had journal integrated publication model. This was done in collaboration with IEEE Design and Test of Computers. So the proceedings of this year's conference will be published by this journal. We received almost 30 complete submissions. This is compared to last year, a 35% increase in the number of submissions. Out of these 30 submissions, we accepted 8 papers. This is 26% acceptance rate. And we accepted 1 short paper, which will not show up in the proceedings, but they will have a presentation in the conference. Of course, this is a journal publication model. So accepted papers went through 2 rounds of peer review, and each paper received a total number of 4 reviews on average. So just some logistics about the conference. Now, this is the 3rd virtual NOCs conference. I hope to see everyone in person next year. So we have the conference going on today and tomorrow. Both days are going to start at 2 p.m. UTC. I'm sure everyone has used Zoom for the past few years for obvious reasons, but please make sure to mute yourself during all the talks. If you have any questions during the talks, feel free to type those questions in the chat, and then the session chair will read those questions to the speakers. After the talks, please feel free to raise your hand or ask to be unmuted, and then we will let you to basically ask your question. This is just a quick overview of the technical program, so today and tomorrow. So in general, we have 2 amazing keynotes, 3 regular sessions on different topics related to NOCs, 2 exciting special sessions, and a very interesting panel for the anniversary of NOCs. I would like to invite my colleague Mikhail to give you more details on the program for this year. So Mikhail, you can go ahead and share your screen.
Perfect. Can you see my screen?
Yes.
Okay, so thanks a lot, Mahdi. My name is Miquel Moretó. I'm a team leader at the Barcelona Supercomputing Center in Spain, and I have been the program co-chair together with Mahdi. So as Mahdi already said, we have 2 keynotes planned for this NOCS conference. Today we have the pleasure of having Professor Marilyn Wolf talking about networks on chips and IoT systems. So this keynote will be just after these opening remarks. And then tomorrow at the same time, so 2 p.m. UTC, Professor Bill Daly will talk about will give us some reflections on the last 21 years of working on NOCS. So please stay tuned and attend this keynote that I'm sure that will be fantastic. Then we have two special sessions. The first special session will happen today at 3:20 UTC. This will be after the keynote. And basically, it will be about design challenges of intra and inter-chiplet interconnection. This is a very hot topic nowadays, so please participate. And tomorrow we have the second special session. It will be at 4 p.m. UTC. And in this case, it will be about electronic, wireless, and photonic NOCS security, challenges and countermeasures. At the end of the conference, on the second day at 5:10 p.m. UTC, we'll have a panel that is going to be a retrospective of the 15++ editions of the NOCS conference. As you know, this year we are in the 16th edition of NOCS. We were supposed to organize this panel last year, but due to COVID restrictions, we couldn't do the in-person symposium. This year we were supposed to do a full in-person workshop in China, but in the end we ended up doing this hybrid symposium. But we decided to go ahead and do the panel because there are lots of things to discuss about these 16 years of NOCS. So we have these fantastic panelists, Professor Radu Marculescu, who is in charge is the organizer and moderator of this panel, and we will have 4 panelists: Professor Bildali, Professor Axel Janch, Dr. Michael Kishinevsky, and then Professor Yumi Togras. As I said, this will happen tomorrow at 5:10 p.m. UTC. And also, among the 8 papers that we accepted, we selected based on the ranking, on the average grades that they received. We selected 2 Best Paper Award candidates. The first one will be presented today in the regular session 1, and the title is Traversal Packets, Opportunistic Bypass Package for Deadlock Recovery. And the second one will be presented tomorrow in the 3rd regular session with the title of RB OLIDs, a worst-case reorder buffer size reduction method for 3D NOC. So please attend these presentations because I'm sure that you will enjoy them. Okay, now we are finishing the remarks. We would like to acknowledge multiple people. First of all, ESWeek organization. It has been a pleasure working with you. The IEEE Design and Test journal. So Professor Parta was our contact point, and he helped us a lot in the organization of this special issue. Special thanks to all the authors and participants in the conference. To the organization committee, Magdi and I have received a lot of help from all of you guys, so thanks a lot for all your help. And finally to the TPC, because they have worked a lot in the review process. They were delivering all the reviews in time, so it was a fantastic experience. And here you can see the list of all the reviewers. So it has been a great experience, as I said. And with that, I would like to thank all of you. And I think, Magdi, you can continue with the introduction of the first keynote speaker.
Yeah, thank you, Mikhail. So let me just go ahead and do the introduction. So our first keynote speaker, Professor Melon Wolf. She's a professor of engineering and director of the School of Computing at the University of Nebraska, Lincoln. She received all her degrees in electrical engineering from Stanford University. Before joining University of Nebraska at Lincoln, she was with Bell Labs and then a faculty at Princeton, and eventually a former distinguished chair in embedded computing systems and GRE eminent scholar at the Georgia Institute of Technology. Her research interests include cyber physical systems, Internet of Things, embedded computing, embedded computer vision, and VLSI systems. She has received multiple awards for her groundbreaking research and educational contributions in these areas, including the IEEE Computer Society Good Memorial Award, the ASEE Terman Award and IEEE Circuits and Systems Society Education Award, just to name a few of these awards. She's a fellow of the IEEE and ACM and a Golden Core member of IEEE Computer Society. Today, she's going to talk about networks and chip and Internet of Things systems, which I can't wait to hear more about it. Melon, please feel free to share your screen, and we're all ears to hear your interesting talk.
Thank you so much, Madi.
Sure.
Appreciate it. By the way, I designed that NOCS logo for the first time we held NOCS.
Wow, I didn't know that.
Yeah. So. Okay. Hopefully, I've shared the right screen. Is that correct?
Yeah, well, we are not looking at the presenter. Well, we're looking at the presenter mode, not
okay,
the...
so I didn't share the right screen.
Yeah.
How's that?
Just give it a second. Yes, it's all perfect now. Thank you.
Okay, great. Well, thank you so much for inviting me. It's great to be back at NOCS. We held the first NOCS at Princeton, and I think it's had a wonderful history. So, like to take a larger view of how network on chips help us with what I consider to be an important class of applications, which is IoT systems. So I'll start out by looking at the promise of really large-scale Internet of Things systems. Then spend a moment looking at how you might design an IoT node and what its requirements are in order to enable us to build these very large-scale IoT systems. Look more particularly at the role VLSI technology plays, and then tie it together with some implications for networks on chips. So I generally prefer to use the term IoT system rather than the Internet of Things. We generally are designing, in a lot of cases, we are designing specific networked systems to do particular tasks. Okay, there is also part of the derivation of this comes from the idea of smart things and being able to track what's in your refrigerator and what's lying around your desk in your office and all that sort of thing. But there is another very important category of networks of sensors that are designed, in which the network is designed for particular applications. Okay, I take a broad, generous view of what IoT means, and while I think that the emphasis is usually on sensing, this might include some actuation as well. Once again, I take a broad view of the network side. A lot of these connections are wireless, but they don't have to be. Okay. There may be reasons why, for power consumption, for bandwidth, or just for convenience, it might make sense to use wired connections for some nodes. Although it's surprising how much wireless pops up. I went to a talk at a jet engine conference in which someone described their use of Bluetooth to monitor inside the middle of a jet engine. Now, this was on a test stand. They were not flying an airplane using Bluetooth, but I was still surprised, and I asked, they said, well, Bluetooth was effective for what they needed, and it was easy, and getting a wire into the middle of a jet engine that's trying very hard not to melt itself isn't worth the effort. So wireless provides a lot of capabilities. Okay. The network configuration on these IoT systems is, on the one hand, long-lived, but on the other hand, it's going to evolve precisely because it is long-lived. The idea that we have a fixed configuration that lasts for years or decades just doesn't pan out. Some nodes are going to die because of age, damage and so forth. They may be replaced, they might not be replaced. Also, the network may be upgraded and reconfigured, partly because of changes in technology, the retirement of 3G being a prime example, but also because we want to add new capabilities, okay? But I think that the way I think of these is that the network is the sensor. A lot of what people call IoT today is a single node. And while those can do useful things, I think that we get a lot of new capabilities by combining sensors. And we can combine the data they generate over both time and space, okay? And this is an example of emerging characteristics that we can do things with large-scale networks that we can't do with a collection of isolated networks where we don't jointly analyze them. Okay, so one of the themes that underlies this is what the MEMS folks call the trillion sensor world. So this makes sense because we have, thanks to MEMS and other technologies, we have the ability to measure all sorts of modalities. There's examples, accelerometers, temperatures, chemical compositions, image sensors, just all sorts of things, okay? Then you add on the fact that we can do signal processing and machine learning on board. And I'll talk later about efficient machine learning that enhances the power of these nodes and motivates us to use more sensors. So we have a combination of sensors with processing, storage, and networking that all help us build more powerful nodes, but also integrate them into more powerful systems. And this notion of a trillion sensors is not rhetorical, okay? I ran some numbers. So in 2018, the industry put out 5.4 million 200 millimeter wafers per month, okay? Which is a lot of wafers. Do some simple arithmetic, and that says, a whole bunch of small chips, okay? So trillion sensors is a practical number, okay? The question is, what do we do with them? And I think when you're talking about volumes of sensors at that scale, that we are really driven to having not just isolated nodes, but distributed systems in which we integrate data from a whole bunch of sensors. And this allows us to build IoT systems of much larger scale. As one example, we're working at the University of Nebraska, along with several other universities, on ways in which we can use sensor networks and artificial intelligence to help farmers and foresters deal with the environment, okay? As weather patterns change, for example, how can we help them understand what's going on and decide how they can make decisions for their farms and forests to ensure the productivity of their land and the stewardship that land will continue to be productive for generations. Okay, so how do you do this? Well, you may need sensors for weather, for example. You also need sensors for what the farmer or forester is doing directly, how much water they're putting on, how moist their land is, the effects of fertilizers and so forth. But also, you want to understand how those fields and crops relate to the larger economic system. So logistics will factor into how they do things. The state of transportation systems. Just last weekend, driving through the country and saw some huge tractors on these small country roads. Those tractors took up, well, probably cost $500,000 a piece, and they're driving them from plot to plot on the roads. If the road is in bad shape, they would have to change their plans. Okay, and there are larger economic effects that may play into this. So we have to be able to not just grab data, but grab it from very large areas and deal with it over time so that we can see trends. So imagine, just for starters, turning the state of Nebraska into an IoT system. Okay, so the state, if on a diagonal, is probably a 9 or 10 hour drive from Falls City on the southeast to Crawford and Harrison in the northwest. Okay, pretty big state. Let's think about how we might instrument it and what we need to instrument. We have roadways that we need to keep track of to see how well traffic is moving. We also have major railroads through the through this part of the country. The Transcontinental Railroad established one of the paths that's still used today. And of course, we have waterways. We have establishments in large cities and in some very rural areas. So we have all sorts of sources of information, and we have all sorts of things we want to understand, right? So we have a whole bunch of sensors, direct physical sensors. We might get information from information systems, for instance, from the industry in this area, looking at not only agriculture, but critical infrastructure, emergency response, the communication systems, gather those in a network, do a whole bunch of computation, some of it closer to the edge or at the edge, some of it in the cloud, and be able to make recommendations and also send alerts out when things are noticed. Okay. So just doing that for the state of Nebraska would give new information and also combine existing information from a whole lot of sources, and would give a more holistic view of what's going on. Now imagine doing that across the country or across an entire continent. Okay, those are some pretty big systems. There are other ways in which we can make use of sensor technology to help us build interesting systems. This is an example that I put together a couple of years ago, exploring the idea of what we could do with a embedded computer vision that was cheap enough that we didn't have to worry about protecting it too much, right? So in the limit, we have a smart camera system that is disposable. And if we want to do that, then we have to be able to have the system organize itself, because we're not going to put a lot of effort into placing cameras in particular places. When we, for instance, instrument a building to see how traffic patterns emerge, we think about where the camera should go. But there are circumstances in which we don't have the time to do that. And so we need more self-organizing camera systems. So this is an example of a scene. At the top here, we actually see two different images that with some overlap. Okay, so if you look carefully, you'll see that the building that's in the center of the image on the left-hand side is only on part of the image on the right-hand side image. So these circles with the pointy things are features that were identified by the SIFT algorithm, and then there's a matching algorithm that you can use to establish a correspondence between those two images based on a whole bunch of features. The result is at the bottom of the screen, in which there are three images that comprise this, and the circles of different colors show features that come from the different images. So these are fairly simple grabbed shots that were combined into a panoramic image that isn't perfect, but it's not bad. And so that shows that it might be possible to build relatively inexpensive cameras that can figure out how they relate to each other in a scene. My student Deep Samal and my colleague, my Georgia Tech colleague, Shaibal Mukabhedi, and I looked at a more complicated scenario for smart image sensors, particularly ones for autonomous vehicles. This is tracking analysis based on LiDAR. LiDAR is a relatively low resolution, well, it's flash LiDAR at least is relatively low resolution sensing technology, but it gives you some important information, namely depth. And so Deep proposed using two types of detectors, a primary detector that's supervised, and then a mass generator, and fusing the results from those in order to improve the overall tracking results. So this shows you some results from this approach. The top left is the supervised object tracker, more traditional neural network. Top right shows you some masks that were used to detect moving people or objects from the scene. Then this is fused to create the final tracker output at the bottom. Okay. So this is a significant amount of computational LiDAR because it's 3D, requires a fair amount of computation, but this approach is aimed at providing a relatively efficient way of analyzing LiDAR data with useful accuracy. So neural networks, machine learning are critical technologies at this point for the analysis of all sorts of real world data. These neural networks require a fair amount of computation. There are several ways to look at that computation. There's the depth of the network, the size of a convolution window, and the total number of parameters. So this table shows you a couple of characteristics for several popular networks, the convolutional layers and the current fully connected layers. You see that the networks vary a fair amount in these parameters. Okay, and of course, these networks also vary in their accuracy for different characteristics, but they also vary in their computation time. Okay, so convolution is an important operator. On the one hand, convolution offers a lot of parallelism. Okay, we've got windows, and the convolution operator, which we see here, allows a lot of things to be done in parallel. However, neural networks combine these operators in stages or layers, and those data dependencies have to be obeyed. Okay, so there are algorithmic limits to the amount of parallelism that we can extract from a neural network, and we have to obey those, and coming up with neural network architectures that give us satisfactory accuracy while allowing us, the efficient computation is an interesting problem that's been looked at by a lot of people. There are a couple of ways to look at efficiency. One is sparsity. So if you have a 0 parameter for convolution or some operation, you don't need to worry about it. Several methods have been looked at for generating sparser sets of coefficients without seriously compromising accuracy. Okay. And this work's been going on for several years, and this has been shown to work very well. Although there are interesting interactions between the algorithms and the underlying compute platform architectures that suggest that simple methods may cause computational efficiencies that don't give you as much payback as you might like. The other major approach is numerical precision. The FinR network is a tool is one example of a tool that does that. Reduced numerical precision can be used in a number of operations to provide good accuracy with lower cost on the arithmetic operations, and smaller arithmetic operators both can reduce the width of the memory, the data that you need, so you can get more data per access, and also reduce the size of the data path, which allows you to put more data path elements on. Okay, so let's think about the IoT nodes. The classic concerns for embedded systems is called SWaP: size, weight, and power. And those are important in a whole bunch of applications. But there are other concerns. Security is a concern, particularly with nodes that are out in the field and can be physically accessed. Latency is an important characteristic, particularly for closed loop systems. And then duty cycle may be a factor. Duty cycle will affect how we use our energy, how we scavenge the battery usage, and so forth. A lot of IoT nodes are not on all the time. And so design for duty cycle is part of the process of figuring out the trade-offs in the IoT node. So this is a block diagram of a sort of generic IoT node. It's a small but complete computing system. Okay, so we may have only one sensor. We may have multiple sensors. Some image sensors, for example, require a fair amount of data transfer. Others may do scalar data that's done infrequently. Think accelerometers, much smaller amount of data. So the amount of data changes, but then we have a host processor that's going to manage the system operation. And we've got an analysis node that's probably using machine learning. And at some point, the results have to go out to the communication network. So this is a fairly generic computing system, but it is also self-contained. And I think the fact that it is self-contained is what gives us both the challenges in designing these things and the opportunities. Okay. Now today, a lot of IoT devices or IoT nodes are built as printed circuit boards. Okay, printed circuit boards provide us a lot of flexibility. We can design a whole bunch of different components. Cost, though, is in a range that makes it less likely that people will deploy these extremely large IoT networks. So we can build some fairly cheap printed circuit boards, but some of these boards are hundreds of dollars. Okay. And the more you spend on a node, the less likely you are to put out a whole bunch of these nodes. And there are applications in which a bunch of cheap nodes, even if they're less reliable and less accurate, can be their data can be combined to give us useful information. Okay, so I think there are reasons to look at technologies and design methodologies that will allow us to build considerably cheaper IoT nodes. So what if we could build IoT nodes in the cost range of 1 cent to maybe $10? I think that would open up some interesting applications, and it poses some significant challenges. Let me just share with you one frustration that we found in some current technologies. My student Krishna Muva here at Nebraska and my colleague Professor Justin Bradley and I have been working on drone-to-drone chasing as a motivating example for embedded computer vision and intelligent autonomous vehicles. So started out with a simulation-driven system. You see the block diagram here using AirSim, and then Krishna put together a flying example of this. In order to get a flyable system, he had to put together, and to do so in a finite amount of time, rather than spending a decade building all sorts of different things. He ended up taking an Intel compute node, one of those little IoT sticks, then plugging it into a Raspberry Pi, and then plugging that Raspberry Pi into the UAV controller. Why? Well, the deployable neural network that we had was on an Intel compute stick, but the Intel compute stick is not supported by the ROS deployment that we have on the controller board on our UAV. That ROS board, however, does support a Raspberry Pi, and the Raspberry Pi does support an Intel compute stick driver. So by transitivity, we can connect the Intel compute stick back to the UAV, but it's not pretty, okay? It would be nice to have design methodologies and technologies that would be a little less kludgy. Okay, so back in the 20th century, when I was at Bell Labs and when I was a younger professor, we had a significant culture of Asic design, application-specific integrated circuit design. And this was sort of an evolution in technology that answered some of the limitations of PCBs. So this was based on, instead of using printed circuit boards to combine a bunch of components to build a functionality, we would use silicon integrated circuits. Okay, so for example, at Bell Labs, we had switching systems that would fill an entire room. A given function might be embodied on a printed circuit board. If you could build an ASIC to do that board, even with the cost of design, it was cheaper to use the ASIC than to build the PCB. Okay. But making that happen required better design automation on the physical level and eventually at the logic design level. In PCBs, you're using larger scale components in order to build these circuit boards. In the ASIC world, we use standard cells, a lot of gate level integration stitched together with place and route, and then of course macros for certain functions. Okay, so even though silicon fabrication was more expensive than printed circuit board fabrication, this solution, the overall solution, was a cost reduction. It was cheaper. Okay, we do less of that today. Okay, so how do we develop and promote an ASIC culture for this IoT era, right? Because IoT has some of the characteristics that we saw before. We have a bunch of different functionalities that we want to be able to implement at low cost and at scale. Well, some of this is going to be based on new technologies, but we also need to leverage mature technologies for fabrication and also for design tools. We'll use stock IP blocks implemented on some amount of stock silicon, but we also need to be able to customize modules, because by implementing only the functions that we need, we can reduce area and reduce chip cost. And I think part of this is cost-effective networks on chips, right? So networks on chips that make sense for systems that have reasonable but not ultra high performance computational needs, and are looking at very low power levels, and being able to crank out a whole bunch of different variations on a theme. Okay, so I'll talk about two ways we might get there. One is looking at single chips, and the other is a chiplet-based approach. And I think that those will require somewhat different approaches. But first, let's look at the cost side. These are two different sets of data from the press that tell us about the sweet spot in semiconductor technology that I think motivates IoT as an important market for the semiconductor industry. On the left hand, we see this picture from NVIDIA that came via the Extreme Tech website. And we see that the y-axis is normalized cost per transistor, and we have curves for different technologies. Historically, as we went to more advanced technologies, smaller transistors, the cost per transistor went down, but that trend has flattened out to a large extent, right? So we get to a point at which a node that is not the leading edge node is in fact the most cost effective technology, and this data suggests perhaps around 28 nanometer. That's where it is. The right hand side is some calculations by the retired engineer feed that was passed on by Tom's Hardware. You look at the price per wafer, a fabricated wafer over 15 years worth of technology went up by about a factor of 10. Okay, now you have to keep in mind that I'm pretty sure that the wafer size increased during that span, so that would account for some of that, but not all of that increase. So once again, mature technologies have their place, and mature technologies are well suited to at least play a role in IoT systems. So you may ask, well, how do you get to these relatively cheap nodes? I did a few calculations using Professor Caselin's cost estimator, which suggested that 1 millimeter by 1 millimeter die has a manufacturing cost of something like $1. How many transistors is that? Well, that's quite a few transistors. And even a very small chip can support a significant number of transistors. Okay, and if you're worried about the number of transistors there, just think about the Intel 4004. Think about how many transistors that had and what people were able to do with it. Okay. Of course, packaging is also important, but even in a single chip system, you can build a single chip system that is very inexpensive, that also provides useful functionality. And I think that the DARPA SHIELD program gave a very good example of that. They were looking at an extremely low-cost chip sort of in the 1 cent range that they could attach to other components in an electronic system to provide ID tags, to help trace the provenance of components and show that components were not fraudulent, for example. So they actually used a 14 nanometer technology for this. And this little tiny chip includes a CPU, it includes some communication, which I believe is near field, a little bit of one-time programmable memory, a physically unclonable function, analog to deconverter, power conversion and management, RF coil, and a temperature sensor. So this was designed to be a system that would both provide an ID information using secure technologies that would allow a user to scan the chiplet and get some ID information to verify that provenance, and also some technologies to detect tampering and indicate when this tag had been tampered with. Okay, very impressive amount of stuff on a very small chip, and with some packaging that enables this mission without costing a lot of money. Okay, so an alternative is chiplets, which have been extremely successful in the larger scale systems. Can we use chiplets for low cost IoT systems? Well, it's going to require some interesting technologies, but I think that's an alternative that deserves some attention. So what are the case for chiplets in IoTs? Well, you've got a very large market, and chiplets should encourage mix and match systems, right? So you can make a lot of variations with less design effort and by leveraging manufacturing volumes also. We saw that there's a block diagram for an IoT node that's fairly generic, but you might put different combinations of things into that generic block diagram. Chiplets are ideally suited to mix and match design. And you need heterogeneous technologies, MEMS, analog digital, memory storage, RF. Once again, chiplets allow you to mix and match. IoT systems do not always need to run at the highest possible clock speeds. You know, you're doing a fair amount of computation in some cases, but you don't necessarily need to run at bleeding edge clock speeds, which may allow you to use less aggressive technologies, certainly in parts of the IoT node. What are some arguments against chiplets? Well, can you make it cheap enough? I don't know the answer to that right now. But you have to come up with an IoT fabrication technology for these substrates that really helps you hit a cost target. You think about commodity components, we would have to develop a market for chiplet style components that we could use in IoT systems. Just taking existing flash and DRAM wouldn't work very well. Depending on the substrate, you may see increased power consumption in some cases relative to single chip technologies. You have to think about environmental ruggedness, and the overall wireless performance and the overall power consumption may be a factor that limits the scope of this kind of system and how cheaply you can make it. Okay, so I think there are questions to be answered, but I do think that we need to explore IoT as an example of the new ASIC and see what combination of manufacturing technologies and design technologies we need. Okay. We also, another factor also is that depending on the technologies, we may see a combination of lower performance and somewhat higher error rates, which might mean a lower payload. Okay. So when we go back to our IoT block diagram, some of the parts of this system will require higher clock speeds. But then there's a system aspect that may require, may need less clock speed. And this is a lesson we see from traditional computer systems that would play out at this scale of smaller, more tightly integrated systems. And so we may have a more traditional NOC for the computational core, but we need to think about using NOCs as next generation embedded fabric buses, right? In a lot of more traditional systems, we see high performance buses and lower cost buses. Networks on chips may need to span that as well. There are a whole bunch of legacy buses out there, many of which date back to the 20th century, okay? And so when we think about using NOCs as a next generation system fabric, we need to think about supporting abstractions in the network, which not all these legacy buses do. I think we need to think about security, which I'll get to in a minute. And we need to be able to synthesize fabric implementations that will support the features we need and not burden us with overhead for features that we don't need. And that's an advantage that we have with perhaps with new technologies that wasn't so apparent in old school systems. So I think that IoT node security is important because a lot of these nodes are going to be out in the world where they are physically accessible, and they're vulnerable to a wide range of attacks. They're also vulnerable to a range of environmental disturbances that aren't attacks, but will still cause problems in the network, okay? So you can imagine attacks or problems related to temperature, to moisture, to electromagnetic effects, and so forth. As we go to systems that have several components integrated, perhaps with a substrate, that will make it somewhat easier for outside people to probe those signals and figure out what's going on and perhaps modify the system. So I think that secure IoT system integration networks is going to be a useful topic for the future. Okay, so remember that in IoT, the network is the sensor. Okay, we want to combine information from a whole bunch of sensors over time and space. But we're going to do that using onboard processing as well as communication. In order to make these large networks happen, we need inexpensive nodes, okay? And inexpensive nodes are going to require leveraging both manufacturing technologies and adapting design methodologies. And NOC is one of those design methodologies. So we need to be able to support a wide range of components within the IoT node, which is itself a complete self-contained computer system. And we need to leverage the best of standards along with customization that allow us to manage cost, implementation costs, and capabilities. Very good. So since I'm broadcasting to you from the state of Nebraska, let me close with this image of a steak that was from a cow, beef cattle that was grown right here on the University of Nebraska. So thank you very much. Questions?
Oh, thank you so much, Melon. I didn't have breakfast, so I'm now more hungry. I appreciate it. So questions, everyone. If you, Abhijit, I'm not sure if we can unmute participant, but I think that's possible, right?
Yes, if you see someone raising hand, then you can unmute them, yes.
Okay, sure. So any questions from the audience? Oh, there is one. Sergi, please go ahead.
Hi, first of all, thank you very much, Melon, for being here today and delivering this very nice keynote and with this very nice end of the talk. My question would be, now that you know that there's a standard going on the chiplet interconnect, this UCIe coming up for chiplet to chiplet interconnect. Do you think that's gonna do some good in this direction that you were saying? Do you think that's gonna give some boost to IoT platform designers that wanna use this chiplet paradigm?
Well, yeah, I've looked at that some. I don't have a definitive answer. I've looked at that some. I'm a little concerned that to get to really inexpensive nodes, that the current, a lot of current design technologies are not going to be enough. Okay, so I don't know specifically whether the existing network integration standards are going to be good enough, but think about what it's going to take to get to a machine learning system that costs $1. Okay, we're going to be dealing with very, sophisticated computation, but using machine learning methods that are very efficient, right? Small values, relative, interesting data access patterns, and then integrating with sensors at a very low cost. Okay, the chiplet efforts so far have gone toward higher end systems.
Thank you, Marilyn. Just a follow-up question. So looking at how cost is important for these IoT nodes, I'm basically going to maybe repeat what Sergey asked, just from another perspective. Do you think we will ever see chiplets to be used, or chiplet technology to be used to design IoT nodes?
Once again, I don't know. I've worked with several of my friends over the summer to write a proposal that to address that very issue. Once again, I think that it's going to have to be noticeably different from the chiplet technology we see on our laptops. Okay, but I think it's worth a try. Okay, and there may be only a couple of chiplets, right? The interconnect is going to be between chiplets is going to be probably considerably lower performance, so system level partitioning is going to be important. Okay, but it seems to me that IoT is a textbook example for why we should do this, right? Because the reason we use boards today is that we have all sorts of different devices that require different manufacturing technologies, right? Mm-hmm. And people have gotten pretty good at designing small boards, but can we take this to the next level, right? So one of my colleagues said a long time ago, a system on chip is everything you need to build a system except for the other stuff you need to build the system, right? And you continue to look at, take apart your cell phone or a lot of things, and there are a whole bunch of chips in there. Okay, some of that we could maybe solve with fabrication technologies that allow us to combine certain things, but also we're probably going to need heterogeneous technologies forever. What can we do in packaging and system integration to lower it? And I don't, once again, have the full answer, but I think we need to try. And also there is the issue of scoping the node, right, as part of a system design process, figuring out how simple a node we can get away with, in order to give us the network capabilities we need. If the network is the IoT system, we don't necessarily have to put everything in the IoT node.
Yeah, thank you, Marilyn. Well, there's a question in the Q&A box. It says, thanks for your keynote talk. How do you think about the advanced package and extra area overhead coming from the chiplet interconnection and D2D interface? I think
once
such
again,
overhead,
sorry.
And then it says, I think such overhead may reduce the chiplet benefit. Thank you.
Well, yeah, I mean, as I say, the current chiplet technologies are designed at a different price point and a different performance point. Okay, can we come up with a manufacturing technology that allows us to hit a significantly lower price point. I think it's worth trying, but that also will probably require repartitioning the system, right, in a way to work around the limitations of the packaging technology. We may have to put up with a very simple, relatively low performance packaging technology and architect the internals of the IoT node. And as I said, figure out what we want to put in the node and what we want to put elsewhere in the network.
Yeah, that makes sense. Thank you. Other questions, everyone? Well, I do not see other questions. Once again, thank you so much, Melon, for the great keynote. I think we all learned a lot.
Thank you. Thank you so much for inviting me. Live
Yeah,
long and prosper.
Thanks. You too.
Okay, take care.